Section 3.1 is the only section we're going to cover in Chapter 3, and this is on the binomial distribution. This entire chapter is devoted to discrete distributions. So we are only focusing on discrete random variables in our binomial distribution. And you'll discover pretty quickly that we have already done problems that qualify as binomial distribution problems when we were looking in Chapter 1. This is when our outcomes only have the option of either heads or tails. You roll an even number or you roll an odd number. So those are both examples of even odds, or what we might call a symmetric distribution. But we also looked at some other problems where maybe it wasn't always symmetric. It wasn't always that the odds were exactly the same. So before we can understand what a binomial distribution is, we have to first talk about what a Bernoulli variable is. And that's exactly the type that I was just mentioning with our coin flips or our die rolls, where we're looking for an even or an odd number. And they're our most important kind of discrete random variable because they happen so often. And these are the types of discrete random variables that can only take on two values. Such a random variable can be used to model the outcome, like I said here, of coin tosses, whether an item is defective or not, or any other process that has only two possible outcomes. Typically, we will label the outcomes as either 0 or 1, where 1 we will define as our success, and 0 we will define as our failure. It doesn't mean that it's necessarily a failed product. In the case of when we were looking at our defective products, a 1 would be the success would be that, yes, it's defective. So that is all about a state where we're just simply labeling one of them as 1 and the other one as 0. So typically when that happens, the random variable is then defined by the parameter p that has to still be between 0 and 1 inclusive, which is the probability that our outcome is from state 1, not from state 0. And again, that goes back to when we were looking at the number of defective items in a shipment. I think we looked at hard drives in an earlier section. And in that section, a success in this case, or a state 1, would be that we found a defective hard drive, because that's what we're interested in measuring here. So these types of simple random variables are known as Bernoulli random variables. And their expectation then, or their mean, is found the same way we find all of our other discrete random variable expectations, which is each state times its probability. So we have 0 times its probability, the probability that x equals 0, plus 1 times the probability that x is equal to 1. Our discrete random variable takes on a success. When we add those up, we find out that the probability of a success we're calling p, and if the total of all of the probabilities still has to be 1, then our probability of x being 0 has to be 1 minus p. It's the complement of p. So what ends up happening here is now we find that we have 0 then times that 1 minus p, which is our probability for 0. Right? We can call that p sub 0. And then we've got our probability p for our success, which we would have in other discrete random variables that have multiple states. We would have called it p sub 1 or p sub 2 or 3 or 4. Here we only have 0 or 1, so we're simply going to call our probability of success p, which is state 1, which makes the probability of state 0 1 minus p. Again, back to the complement. So what happens is when we do 0 times 1 minus p, and then we add to it 1 times p, we're just left with p. So our expectation of a single Bernoulli random variable is simply p. Let me find my highlighter there. There we go. So our expectation of a simple Bernoulli random variable is just p. And because then we can also find our expectation of x squared in the same way, we can then find out that our expectation of x squared instead now is 0 squared times our probability that x is 0 plus 1 squared times our probability that x is 1. Which means here we're saying that we have 0 squared times 1 minus p plus 1 squared times p. And when we add it all up, again, this time we end up back at p. So when we're looking at finding our variance, remember variance is e of x squared, so our expected value of x squared, minus our mean e of x, the whole quantity squared. So in this case, we would have p for our e of x squared we just found was p. So that's this guy. And then we found earlier that our expectation of x, our mean, was p. When we square it, it becomes p squared. And in the end, what we end up with is that our variation of a Bernoulli random variable is p times the quantity 1 minus p. So the probability of a success times the probability of a failure is our variance for a single Bernoulli random variable. And of course, I have this all put in a box right below where I always summarize things for you. So let's talk about what we see in our box here, our definition. It says a Bernoulli random variable, right, our Bernoulli random variable with parameter p that's between 0 and 1. This is what happens when I write things too late at night when I have a migraine. Sorry about that. Between 0 and 1. Takes on the values of 0 and 1 with the probability that x is 0 being 1 minus p. The probability that x is 1 is p. So again, these were what we called our successes or failures. So this was the probability of a failure, and this was the probability of a success. So the easiest ways to think about these probabilities. The expectation and variance were given, which we just found above. Our expectation was p, and our variance was 1, or p times 1 minus p. So what then is this binomial distribution? Well, a lot of processes can be thought of consisting of a sequence of Bernoulli trials, that is, experiments based on Bernoulli random variables, experiments with only 2 outcomes. In such cases, a random variable of interest is the number of successes obtained within n trials. So now we're adding in a parameter that we're going to run n trials, where a success here is defined in the context of the problem or the experiment. Like I said earlier, when we were looking at the probability that we were trying to find defective, I think they were hard drives, in a box of 10 or 15 or whatever we were looking at, the success would have been a defective hard drive. So it's all dependent on the problem you're looking at. If we're flipping a coin, maybe you're interested in the number of heads. Maybe the next time you look at it, you're interested in the number of tails, so you would change what you consider a success to be in each case. If we run these n experiments, then we can start to build what we are going to call our binomial distribution. So if we call our random variable x, and it is a Bernoulli random variable that only has 2 possible outcomes, but we're running n trials using this random variable, then we call our random variable a binomial random variable. If n independent Bernoulli trials, x1, x2, all the way out to xn, are performed, each with the same probability p of recording a success, then the random variable x by itself is the sum of all of those experiments. And we say then that that creates our binomial distribution. So our binomial distribution is written as x, and then you see this little tilde sign. It just means that x is being represented by a binomial distribution of n and p. The parameters of this distribution are n, the number of trials, and p, the probability of success on each trial. So here, sometimes I will also say I've seen these ones as x is described by, and sometimes it says binom of n, comma p. So if you're looking in a different text that's also talking about statistics and you see it saying binom instead of just plain B, that's probably why. And remember here, N is our number of trials, number of our Bernoulli trials, and P is the probability of success. I can spell, let's see here. Probability of a success. The thing that differentiates here the binomial random variable from the Bernoulli is that a Bernoulli random variable can only take on state 0 or state 1. However, the binomial random variable is the one that counts up the number of successes throughout your n trials of your Bernoulli random variables. So what that means is your binomial random variable x then could be 0 because maybe you never got a success, or maybe out of your n trials you got 1 or 2 successes, or 3, or maybe 8 or 10, or however many you ran, which would be n. So the values that x can take on are integers between 0 and n. You either had no successes or you had all successes or any number in between the two. And it counts the number of successes in all of our n trials. So since the Bernoulli random variables each have an expectation of p, the expectation then of a binomial random variable modeled by n trials each with a probability of success p can easily be calculated as the expectation of each one added together. So if we look at it, we have our expectation now for our binomial is the expectation of 1 plus 2 plus all the way up to the expectation of our final x sub n. And each one of those has a probability of success p. They each have an expected value of p, a mean of p, which we saw on the previous page. So when we add up n times p, then that's where we find our expected value of our binomial random variable. So we added up p n times and ended up with our expectation being n times p. In a very similar fashion, when we start adding up all of the variations here of x, then what happens is we had our variation for each random variable was p times 1 minus p, which then means if we add them up n times, right, we add up each of those variations n times, and we have p times the quantity 1 minus p plus p times the quantity 1 minus p n times. So we end up with a variation that is np times the quantity 1 minus p. So we have p times 1 minus p, that variation before, times the number of trials, which is n. And of course, like I said before, I have it all summarized in a table for you. So if we consider an experiment consisting of n Bernoulli trials that are independent and that each have a constant probability of p successes. So we have all of these Bernoulli variables that we're running these Bernoulli trials on. They can either take on a 0 or a 1, and the probability that they take on state 1 is p. They have to be independent of one another. Again, think coin flips or die rolls. And they have to have the same probability of a success every single time. Still holds true for our coin flips and our die rolls, as long as we have a fair coin or a fair die. Then the total number of successes, x, is then a random variable itself that is called a binomial random variable, and it has a binomial distribution with the parameters n and p, which we said is written as x is represented by b of n comma p. And again, like I said in some text, you might see it as x is represented by b, a binom of n comma p. It's the same idea. The PMF here, the probability mass function, again, we know it's a PMF because we have a discrete random variable, not a continuous random variable. So our discrete random variable here has a probability mass function given by the formula. P of x equaling x is given as n choose x times the probability of success raised to the x power and the probability of failure raised to the remaining trials, meaning our number of failures. So really what we have here is we have the combination of n choose x. So out of our n trials, how many ways can I choose 3 successes? How many ways can I have 3 successes? And then my probability of success raised to that power of 3, which we're going to look at a couple of examples of, I'm just picking 3 for this theoretical example. And then we would have our probability of failure, 1 minus p, raised to whatever n minus 3 is, however many trials we had. If we had 10 trials, then I would have 10 choose 3, our probability of a success raised to the third times our probability of failure raised to the 7th. The 2 exponents here should always add up to n because you need to have accounted for all of your numbers of failures and all of your numbers of successes. Remember, this is pretty much a binary example. It is either 0 or it's 1. There's nothing else for it to be. So it has to be included either as a failure or a success. When we have this, and remember x then can only be as big as the number of trials, so x can only go from 0 to n. And when we find this, we find that still what we found earlier, our expectation of this binomial random variable is n times p, which we found earlier by adding up all of the probability of successes n times. So p was the expected value for each trial when we ran n trials, so n times p. And in the same way we found before, the variation of our new binomial random variable is going to be n times the variation of each Bernoulli random variable, which is p times 1 minus p. Probability of success times the probability of failure. It's just that we're going to add them up n times now, so we multiply it by n. For example 3.1.1, we're going to look at a couple of different probability mass functions and cumulative distribution functions for binomial random variables. So the first one we're going to look at is the binomial distribution that it has 8 trials and a probability of 0.5 that we're going to have a success. So here we have n equals 8, and we have our probability of success is equal to 0.5. Something to think about then is, what is our probability of failure, right? So this is our probability of a success here. So our probability of a failure is also 0.5. So this is what we might call a symmetric binomial distribution. And it's all about that probability. If that probability is 0.5, it's automatically symmetric. And if we look at our PMF function, it is exactly symmetric. We have 0.004 on the ends. We move in by 1, 0.031, move in again. 0.109, move in again. 0.219, and in the very middle we have 0.273. So that point in the middle, because this is symmetric, is going to be our mean. And if we calculate it, we would also find that it's our median, because our distribution is symmetric. So symmetric distributions are really useful in statistics. They make lighter work of the things that we need to accomplish because we can get to our answers a little bit faster due to the properties of symmetry. So we'll see that played out here in a couple of these problems. So what is the probability that x equals 3? Well, here we could look at our graph. Our graph tells us, and this is for, right, we have A and B over here. The graph tells us that the probability of 3 successes is 0.219. Now, if I didn't give you the PMF, could we calculate it using the formula? The answer is 100% yes. So let's look at our formula. The probability that x equals 3, meaning we have 3 successes out of our 8 trials. We have a total of 3 successes, means we have to choose out of our 8 trials 3. So just a reminder from chapter 1 in section 1.7 on counting, when we're looking at this sort of notation, that is a combination. So this is 8 choose 3, it's a combination. The order doesn't matter, we just want to know that we find 3 successes somewhere in our 8 trials. It doesn't matter if it's on trials 1, 2, and 3, 1, 7, and 8, 3, 4, 5. It doesn't matter where they occur, we just need to know that they do occur. So we have the combination of 8 choose 3, and then we have our probability of a success, 0.5, raised to the number of successes, which is 3, times the probability of our failure, which is also 0.5, raised to the number of failures, which is 5. So what we find when we have a symmetric distribution is that realistically we have 8 choose 3 times 0.5 to the number of trials n. But this is only true for symmetric distributions. And when we calculate these values, and again, you can use desmos.com/scientific to evaluate your combination here. And what we find out is we have, if you don't want to do it by hand, by the way, you can also do it by hand. But we get 0.219, which is exactly what we found above on the PMF that I provided. This PMF was calculated with all of these formulas in mind. So it's not surprising that our results matched. If we wanted to find the probability that our number of successes is less than or equal to 1, we have to keep in mind that there are only 2 ways for our number of successes to be less than or equal to 1. This means that we have the probability that our number of successes is less than or equal to 1 is the same as saying it's the probability that we have no successes, or, which means add, right? Addition. So we will add the probability that x is equal to 1 success. Those are the only ways for us to get less than or equal to 1 successes. Either we can do 0 successes or we can do 1 success. From the graph, we would say that that is the probability that x equals 0, which is 0.004, plus the probability that it's 1, which is 0.031, for a total of 0.035. So when we use the formula, it should add up to give us the same result. So we would say that this is the probability that out of our 8 trials, we chose 0 successes, and because it's symmetric, it's 0.5 to the 8, plus, oh, didn't mean to include the p, our combination of, out of our 8 trials, we choose 1 success, and our probability raised to the 8th power, again, only because it's a symmetric distribution. This only works with 0.5. And in this case, what do we end up with? We end up with exactly what was on the PMF chart above, which is 0.004 plus 0.031 for a total of 0.035. So if I were to give you a PMF chart, you could read it right off the chart. If I don't give you a PMF chart, then you can use the formula. How do we think this is going to change when we don't have a symmetric distribution? Well, what we're going to find out is that no longer can we just do our 0.5 and raise it to the number of trials, because we don't have the same probability now of failures and successes. Maybe in the first experiment, we flipped a coin 8 times. That was fair. But instead, for the second one, we flipped an unfair coin. And this is our PMF and CDF that are on the right. And you'll notice that a lot of the probability is front loaded. It's loaded into 0, 1, 2, 3, 4, 5, with all these little tiny probabilities out here that we get 7 and 8. They're so much smaller. Even 6 is smaller than 0. Most of our probability is lying at the beginning. And what we find out is this is actually a binomial distribution of 8 trials with a probability of success of 1/3. So this is for C and for D. This one is not symmetric. So we can't just raise our probability to the number of trials. So in this case now, we could look at the chart to figure out the same questions as before, because I'm going to ask you the same things. What is the probability of 3 successes? Well, if we look at the probability of 3 successes in our new random variable, we find out that our probability of 3 successes is now 0.273, which is higher than it was before. But that's also because we have this one more front loaded. We said it's actually going to be a smaller number because there's only 1/3 of a chance of getting a success instead of 1/2, and 1/3 is smaller than 1/2. So we've put more of our probability to the left side of our graph than we did to the right side. So when we find our probability of 0 or 1 successes, it's going to be significantly higher in this second distribution because we have more of our probability again in the lower end of our number of successes. So let's see how these numbers change a little. So if we wanted to find for our binomial of n comma p being 8 trials and a probability of success only being 1/3, what does that look like? When we want to know the number of successes, the probability that with number of successes is 3. From the graph, we know that the probability that x equals 3, we said was 0.273. Let's see what this looks like using our formula. So the probability that x equals 3 now is, out of our 8 trials, we choose 3 successes. Our probability of success is 1/3 raised to the number of successes, which is 3, times our probability of failure, which would be the remaining 2/3, to the number of remaining trials that it wasn't a success on. So a failure, which would be 8 minus 3, which is 5. So we have 8, choose 3 successes, times the probability of success raised to the number of successes, times the probability of failure raised to the number of failures. And when we find this, we do in fact end up at 0.273. So what I'd like for you to do is try to find our probability that x is less than or equal to 1 from the graph and using the formulas. So I want you to pause the video and try to use the formula to calculate the probability that x is less than or equal to 1. Well, I hope that you tried this on your own, and we're also going to look at it together. So if we read from the graph, the probability that x is less than or equal to 1 is going to be the probability that x is 0, which is 0.039, plus the probability that it is equal to 1, which is 0.156. Oops, I think I made a typo there, 0.156. Okay, for a total of 0.195, which is exactly what our CDF chart underneath it tells us it should be. When you look at 1, the accumulated probability is 0.195. We kind of neglected to look at that in the last one, but it's also there in the CDF. The accumulated probability at x equals 1 there is 0.035, which is what we found. So when we looked at an even chance of probability or success, then we ended up with the probability being 0.035 that we had 0 or 1 successes. When we drop the probability of a success down to only 1/3, we find now that our probability of having 1 or 0 successes is now as high as 0.195. So we jump from 3.5% up to almost 20%. So it is a very significant difference. And if we wanted to do this using our formula, then we're going to look at the probability that x is equal to 0 or plus the probability that x is equal to 1. So this is, again, where our discrete random variables make this pretty easy because we don't have anything between 0 successes and 1 success. So here we would have our 8 trials choose 0 successes times our probability of success 1/3 raised to the number of successes 0 times our probability of a failure, which has to be 1 minus 1/3, which is 2/3, raised to the number of failures. If we don't have any successes, all of our trials, all 8 of them, are failures. And then we'll add to it, out of our 8 trials, we choose 1 success, times our probability of success 1/3 raised to the number of successes, which is 1, times our probability of failures 2/3 raised to the number of failures, which is 7. And when we do this, we find that we get 0.039 plus 0.156, which should look awfully familiar. This ends up being our 0.195. For example, 3.1.2, we're going to look at cartons of oat milk. I love Planet oat milk, so you get Planet oat milk as a problem. So Planet Oat determines that there is a probability of 0.261 that a carton of their oat milk is underweight. Suppose that the oat milk cartons are shipped in boxes of 20 cartons. What is the distribution of the underweight cartons in a box? So we have to consider it this way. What are our possible outcomes here? And the answer is it underweight or not? So it only has a chance of being a yes or a no. That sounds like 2 outcomes and a Bernoulli random variable. And if we look at a trial of size 20, aka all 20 cartons of oat milk in a single box, we now have 20 Bernoulli trials. We can test each carton in the box to say, is it overweight or is it not? And in this case, we're going to define our state 1 or our success as being underweight. So we're going to have to write out a few definitions here. So we're going to say that we have a binomial. So x is definitely able to be represented by a binomial random variable with 20 trials. And our probability of success here is going to be 0.261. But we have to describe that this is where our success, right, where successes equals an underweight carton. And you kind of want to think about it in terms of the real world where you go, well, wouldn't that be kind of a failure because they failed to meet their expectation? But what we're interested in is the probability that we have an underweight container, right? An underweight carton. So that to us is what we're interested in. So that is our variable of interest, our measure of interest. And because it's our measure of interest, we're going to call that our success. So you have to remember that every time we do a different experiment, a different trial, that our success is going to be defined by the problem. So in this case, what is the expected number of underweight cartons in a box? Well, here we're looking at the expected value of a Bernoulli trial, like of n Bernoulli trials, which is a binomial distribution. We already saw earlier that the expected value of a binomial random variable is simply n times the probability of success, the number of trials times the probability of success. So in our case, that is 20 trials times our 0.261, our probability of success. So we end up with 5.22 cartons. So what does that mean? That on average, 5.22 cartons of the 20 cartons in a box will be underweight. Well, this is 26%. That's roughly a quarter. So a quarter of 20 is 5. So we're a little bit over a quarter. So this actually makes a lot of sense that it would be a little more than 5 cartons. What would be the variance on the number of cartons that are underweight? Well, our variance here, remember in n Bernoulli trials, is n times the variation of a single Bernoulli random variable, which was p times 1 minus p. So the variance of our binomial random variable is np times 1 minus p. Or we know np already is 5.22. So that's easy. We found that above. And here, we'll write it out separately. But that's probably the easiest way to think about this one. But here, we'll write it out as 20 times 0.261, and then it would be 1 minus 0.261. But again, we know that 20 times 0.261 is 5.22, and our 1 minus 0.261 ends up being 739. So you end up with a variation of 3.858. And this is where we talk about those crazy units. This would actually be cartons squared. And then we need to find our standard deviation here, right? Our standard deviation, which is sigma, right? We had our variation was sigma squared. So sigma here is going to be the square root of sigma squared, or the square root of our variance, or the square root of our 3.858. So our standard deviation ends up being 1.964, and because we took the square root, this is just simply cartons, not cartons squared. So that's how much we can expect our number of cartons to vary for one standard deviation. It's almost as high as 2. Right? What is our probability then that we have 6 underweight cartons in our case of 20? Well, we go back to our formula. Our probability that our number of successes is 6 is our number of trials 20. So out of the 20 cartons, we choose 6 of them to be underweight, times the probability that it's underweight, which is 0.261, raised to the number of times we want them to be underweight, which is the 6. So the number of successes probability of success raised to the number of successes, times the probability of failure, which we already know is 0.739, raised to the number of failures. Well, 20 minus 6 is 14. So in this case, we end up with a probability of 0.178. And again, you can use your calculator or the desmos.com/scientific in order to find that combination at the beginning. And then part E, our last section here, our last part, asks, what is the probability that a box contains no more than 3 underweight cartons of oat milk? So here's what we have to consider. Is it easier to do the 0 to 3 or to do its complement? I hope you said that it's easier to do the 3, because the complement will be 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. That's a lot of calculating and a lot of adding up. So if we stick to the probability of 0, 1, 2, or 3 successes, then we are going to have a much easier time. So the probability that x is less than or equal to 3 then would be the probability that x equals 0 plus the probability that x equals 1 plus the probability that x equals 2 plus the probability of x equaling 3. So in terms of the way we were considering this back in chapter 1, this was the probability of one success, right? Or the probability of no success, or the probability of two successes, or the probability of three successes. So everywhere we have an or, we have an addition, right? We add them up. So now we can use our formula to say that out of our 20 cartons, we choose 0. And then we have the probability of a success, 0.261 to the 0, times the probability of failure, which is a 0.739 raised to all 20. We're saying that all 20 of them fail to be underweight. Plus, now we'll do the same thing. We'll do 20, choose 1, 0.261 raised to the 1, its complement 0.739 raised to the remaining trials, plus 20, choose 2, our 2.261 raised to the 2, our 0.739 raised to the remaining 18, and then we'll also add in our 20, choose 3, with our success 261 raised to the 3 successes times our 0.739, the complement or the failure probability, raised to the remaining 17 trials. So again, remember, your number of successes is given in the formula by 20 choose, and choose the number of successes x. So that's our first exponent. The second exponent is whatever is remaining. Those two exponents have to add up to n. So we end up with probability that x is 0 is 0.0024 plus the probability that x is 1 is 0.0167 plus the probability that x is 2 is 0.0559 and the probability that x is 3 is 0.1185. And when we add them all up, we get a 0.1935. So the probability that we have 3 or fewer cartons that are underweight is 19%. We have a 19.35% chance that we have 3 or fewer underweight cartons by this model.